Tonight, we are going somewhere no spacecraft has ever reached. Not Mars, not Jupiter, not even the edge of the solar wind where Voyager crossed into interstellar space after 46 years of travel. We are going further than that, much further. We are heading for a place so distant that the fastest object humanity has ever launched would need 30,000 years to reach it. A place we have never seen directly, never photographed, never touched with any instrument we have ever built. But it is ours. It belongs to our sun. And it is so vast that once you understand its true scale, the solar system you grew up learning about will feel like a map someone drew without finishing the edges. This is not a story about the planets. Those are the first few rooms of a house that stretches for a light year in every direction. This is a path to where the solar system actually ends. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. There is an image most of us have carried for a long time. You have probably seen it in a textbook, or on a poster in a classroom, or in some animated diagram on a screen. The sun sits at the centre, bright and golden. 8 planets spiral outward in their neat elliptical orbits, each one a little colder and a little darker than the one before it. Saturn with its rings, Uranus tilted on its side, and then Neptune, blue and frozen, orbiting at the furthest edge, the last outpost before the blackness begins. It is a clean image, a satisfying one, and it is missing most of the story. Before we can understand what is out there, really out there beyond the last planet, we need a measuring stick. Astronomers use one called the astronomical unit, or AU. 1 AU is the distance between the Earth and the Sun, roughly 150 million kilometers. That number means almost nothing on its own, so here is a way to feel it. If you got in a car and drove at highway speed, around 100 kilometers per hour, without stopping for a single second, it would take you roughly 170 years to reach the Sun from Earth. One direction. No detours. That is 1 AU. Now start walking outward. Mercury is less than half an AU from the Sun. Earth is at 1. Mars sits at 1.5. Jupiter is at 5. Saturn is at 10. Uranus at 19. And then Neptune, the last major planet, the cold blue giant at the outer edge of our familiar map, orbits at roughly 30 AU. 30 times the Earth-Sun distance. By car, that is 5,000 years of uninterrupted driving. And most people, somewhere around here, draw their mental line. The solar system is the planets. The solar system ends somewhere past Neptune. That is the edge. But here is where the path begins to get interesting. Past Neptune, there is a region called the Kuiper Belt. You may have heard of it. It is a wide ring of icy objects, small frozen worlds and debris, stretching from roughly 30 AU out to about 50 AU. Pluto lives here. Pluto, that small, distant, strangely beautiful world that New Horizons visited in 2015 after 9.5 years of travel, is a Kuiper Belt object. It orbits between 30 and 49 AU, depending on where it sits in its long elliptical path. 50 AU. That feels like a reasonable outer edge, past Neptune, past Pluto, past the Kuiper Belt. Cold, dark and distant. Surely after 50 AU, the solar system begins to loosen its grip and the real emptiness starts. Here is the first crack in that picture. The inner edge of the Oort cloud, the solar system's true outermost structure, does not begin at 50 AU. It begins at approximately 2000 AU. That number deserves a moment to land: 2000 AU. If Neptune at 30 AU is already 5,000 years away by car, then the beginning of the Oort cloud is 66 times further than that. And that is not where the Oort cloud ends. That is where it starts. The outer boundary of the Oort cloud extends somewhere between 50,000 and 200,000 AU from the Sun. Most models place it around 100,000 AU. In terms of light travel time, light from the Sun takes about 8 minutes to reach Earth. It takes roughly 13 months to reach the inner Oort cloud. And to reach the outer edge, light from the Sun travels for more than a year, possibly close to 2. The solar system, by its true gravitational extent, is roughly 1 to 2 light years across. Think about what that means. The familiar image, the 8 planets, the rings of Saturn, the neat concentric orbits, all of that represents perhaps 1% of the solar system's full radius. The other 99% is a vast, dark, barely understood shell of trillions of frozen objects that the Sun still owns, still holds in orbit, still calls its own. That shell is where this investigation is going, but to reach it, to really understand what the Oort cloud is and why its scale matters, we need to first understand the landscape between where the planets end and where the cloud begins. Because that middle distance is not empty. It is a region of objects, structures, and gravitational stories that no school map has ever fully shown. And the first hint of what lies out there came from the most famous small world in the solar system. In the summer of 2015, a spacecraft called New Horizons arrived at Pluto after travelling for 9.5 years. It had crossed more than 3 billion miles. Its instruments had been dormant for years to preserve power, and in the final weeks of approach, it began to wake up and send back the first clear images anyone had ever seen of that distant frozen world. What they showed surprised almost everyone. Pluto was not the dead, featureless ball of ice that many had expected. It had mountains. It had plains of nitrogen ice so flat and smooth they looked almost artificially clean. It had a haze layer in its thin atmosphere, a dim blue ring of light visible against the darkness when New Horizons looked back toward the Sun. It was, in its cold and quiet way, a genuine world. Pluto orbits between roughly 30 and 49 AU. At its most distant point from the Sun, it sits at nearly 50 AU, right at the outer edge of the Kuiper Belt. And yet, as New Horizons confirmed, it is not alone out there. The Kuiper Belt is populated with hundreds of thousands of objects. Frozen bodies of rock and ice, leftovers from the formation of the solar system, orbiting in a wide flat disk beyond Neptune. That disk is real. It has been studied. Spacecraft have flown through it. Telescopes have catalogued its largest members. But it is also, in the context of the full solar system, unusually close to home. Here is the number that changes the perspective. The Kuiper Belt extends from roughly 30 AU to about 50 AU. The gap between the outer edge of the Kuiper Belt and the inner edge of the Oort cloud is approximately 1,950 AU. That gap, that apparently empty space between the two structures, is nearly 40 times larger than the entire Kuiper Belt itself. That is not a small oversight in the textbook map. That is the map missing almost everything. And the gap is not entirely empty. Between the Kuiper Belt and the Oort cloud lies a region called the scattered disk, a loosely defined population of objects on highly elongated orbits that cross or extend beyond the Kuiper Belt. These are objects whose paths were disturbed long ago, pushed into unusual orbits by gravitational encounters with the giant planets. They are the debris of ancient chaos. New Horizons is currently in the Kuiper Belt, still travelling outward, still returning data. But it will not reach the Oort cloud. Not in any human lifetime, not in any mission timeline, not in any planning horizon we can currently imagine. At its current speed, New Horizons would reach the inner edge of the Oort cloud in roughly 485 years. That is a number worth sitting with for a moment. New Horizons, one of the fastest objects ever built, launched in 2006, carrying the best propulsion technology we had available, would need nearly 5 centuries to reach the beginning of the outer solar system. Not the middle, not the far side, the beginning. And just beyond the scattered disk, orbiting in a space that no instrument has ever clearly seen, something was discovered in 2003 that changed what astronomers thought they knew about the solar system's architecture. Its name was Sedna. Sedna was found almost by accident. A team of astronomers using a telescope at Palomar Observatory in California detected a faint, slow-moving point of light in November 2003. It was so distant, so cold and so red that it did not fit neatly into any known category. It was not a Kuiper Belt object. It was not a planet. It was not exactly anything the solar system map had a label for. It orbited the Sun. That much was clear. But its orbit was unlike anything seen before. At its closest approach to the Sun, called perihelion, Sedna comes to within roughly 76 AU. That alone puts it well beyond the Kuiper Belt. But its orbit is highly elongated, stretching outwards to an estimated aphelion, its furthest point, of somewhere around 937 AU. Sedna takes roughly 11,000 Earth years to complete one orbit of the Sun. 11,000 years. When Sedna was last at its closest approach to the Sun, human civilization was in its earliest stages. Cities did not yet exist. Writing had not been invented. At 76 AU, Sedna is already so far from the Sun that the Sun would appear as nothing more than an extremely bright star. Not warm, not golden, just a point of intense light in a pitch-black sky. At Sedna's furthest point, 937 AU away, the Sun's light is so faint that it provides almost no heat at all. The surface temperature of Sedna is estimated at around -240 degrees Celsius, making it one of the coldest objects in the known solar system. But here is why Sedna matters to this story. The problem with Sedna is not its distance. The problem is that astronomers could not explain how it got there. Objects in the Kuiper Belt and scattered disk ended up where they are because of gravitational interactions with Neptune. Neptune's gravity over billions of years nudged and scattered objects outward, deflecting them into different orbits. That process can explain most of what we find out to about 100 or 200 AU. But Sedna's orbit does not touch that region. At its closest, Sedna is at 76 AU, well beyond Neptune's influence zone. Neptune could not have put Sedna where it is. Something else did. The most widely accepted explanation is that Sedna came from, or was scattered into, an inner reservoir of objects that sits between the scattered disk and the full Oort cloud, a structure sometimes called the Hills Cloud, or the inner Oort cloud. A region we have never directly mapped, but whose existence Sedna's orbit effectively requires. Sedna may be the closest object we have ever seen from that inner reservoir. It may be a piece of the Oort cloud that strayed closer to the Sun than the rest. If that is true, then when astronomers found Sedna, they were not just discovering a distant frozen world. They were getting their first glimpse of the cloud that surrounds the entire solar system. A glimpse from 76 AU. And the cloud begins at 2000. To understand what the Oort cloud actually is, it helps to imagine the solar system not as a flat disk, but as a series of nested shells, each one larger than everything inside it combined. Start at the centre. The Sun. Around it, the 8 planets orbit in a flat plane, the same plane in which the original disk of gas and dust collapsed when the solar system formed 4.6 billion years ago. That flat planetary region, stretching out to Neptune at 30 AU, is what most people mean when they say the solar system. Then comes the Kuiper Belt, extending from 30 to roughly 50 AU. Still flat. Still a disk. Still part of the original formation geometry. Then the scattered disk, loosely defined, stretching out to perhaps 100 or 200 AU in some estimates, populated with objects on irregular orbits. Then a gap. And then, beginning at approximately 2000 AU, the first shell of the Oort cloud. This inner region, sometimes called the Hills cloud after astronomer Jack Hills, who proposed it in 1981, is thought to be a somewhat flattened or disk-like structure, denser and more tightly bound to the Sun than the outer cloud. Sedna likely occupies the inner edge of this region. Beyond the Hills cloud, the Oort cloud transitions into its outer shell, and here is where the geometry changes completely. The outer Oort cloud is not a disk, it is a sphere. This is one of the most important things to understand about the Oort cloud, and it is the feature that most clearly separates it from everything else in the solar system. The planets orbit in a flat plane. The Kuiper Belt is a flat ring, but the outer Oort cloud surrounds the solar system in all directions, above and below the ecliptic, at every angle, a nearly spherical shell of trillions of frozen objects, extending in every direction from the Sun. The reason this matters is what it tells us about the cloud's origin and history. Objects in a disk got there because they formed in a disk, or were scattered within a disk. Objects in a sphere got there because they were thrown outward in all directions over a very long time, their orbits gradually rounded by forces that reach into even the furthest regions of the solar system. That spherical shape is not a design feature, it is a record of billions of years of gravitational history, and the outer Oort cloud extends far enough that its objects are barely held by the Sun at all. At 100,000 AU from the Sun, the gravitational pull is so weak that even distant stars passing through the neighbourhood can nudge objects out of their ancient orbits. The galactic environment itself reaches into the outer Oort cloud and shapes what lives there. The solar system at this scale is not a closed, isolated system. It is a structure in conversation with the galaxy around it. One of the most elegant things about the Oort cloud is this. We have never seen it directly. No telescope has resolved it. No spacecraft has visited it. No photograph has captured it. It has never been observed the way we observe a planet or a comet or even a distant galaxy. And yet, among astronomers, its existence is not seriously doubted. The evidence for it is as strong as the evidence for almost anything in planetary science. That evidence comes from comets. Specifically, it comes from a type of comet called a long-period comet. These are comets with orbital periods greater than 200 years, often much greater than that. Some take thousands of years to complete a single orbit, some take millions. A few are on trajectories so elongated that they will pass through the inner solar system once and never return, flung outward by the Sun's gravity on their way out. When astronomers map the orbits of these long-period comets, something becomes clear. Their paths, when traced backward from their current positions through the physics of orbital mechanics, point back to a common region of origin. Not the Kuiper Belt, not the scattered disk. A spherical shell at enormous distance from the Sun, centered on the solar system, extending in all directions. The first astronomer to recognize this pattern was Jan Oort, a Dutch astronomer who published a landmark paper in 1950. Oort analysed the orbital data of known comets and noticed that the distribution of their orbital energies clustered around values consistent with an origin at very large distances from the Sun. He proposed that these comets were being disturbed from a distant cloud and sent inward on their long falling paths toward the light. That cloud now carries his name. The reasoning is similar to the way a detective reconstructs a crime from evidence left behind. You do not need to have been present when it happened. You need only understand the physical laws well enough to trace the path backward. A comet arriving in the inner solar system on a highly elongated orbit, coming from a direction that has nothing to do with the ecliptic plane, is a comet that came from somewhere spherical and very far away. When you map hundreds of them, they all point to the same place. Think about what that means as an act of observation. We cannot see the Oort cloud, but we can see its messengers. Every long-period comet that crosses Earth's sky is a piece of the Oort cloud that has been in transit falling inward for perhaps 1 million years or more. The comet that appeared last century, or last decade, or that will appear next year, began its transit before our species had developed agriculture. We are not watching a comet. We are watching the Oort cloud arrive. A comet does not simply decide to fall toward the Sun. Something pushes it. For billions of years, most Oort cloud objects sit in their distant orbits, frozen, dark, barely moving relative to the Sun, disturbed by almost nothing. Their orbits are stable enough to persist across geological timescales. A comet placed in the outer Oort cloud at the formation of the solar system might sit there, undisturbed, for 4 billion years. And then something changes. The thing that changes is not the Sun. At 50,000 or 100,000 AU, the Sun's gravitational pull is extraordinarily weak. Weak enough that other forces that would be completely negligible closer in, begin to matter. The first of those forces is passing stars. The Sun is not stationary. It moves through the Milky Way on its own long orbit around the galactic center, taking roughly 225 million years to complete one circuit. As it moves, other stars move past it. Not close passes in human terms, not close enough to cause catastrophic disruption, but passes within a few light years that, over millions of years, are close enough to gravitationally nudge the outermost objects in the Oort cloud. Our nearest stellar neighbour, Proxima Centauri, is about 4.2 light-years away. Over the history of the solar system, dozens of stars have likely passed within a few light-years, some possibly closer. Each one, as it moves through the neighbourhood, exerts a small gravitational tug on the outer Oort cloud. A slight change in velocity, a slight shift in orbital energy. Over millions of years, these small shifts accumulate. For some objects, those accumulated shifts are enough to alter the orbit fundamentally, dropping the object's closest approach to the Sun from tens of thousands of AU down to a few AU, or even less. Those are the objects that become long-period comets. Those are the objects that eventually reach the inner solar system. The second force is larger, stranger, and harder to picture. It is called the galactic tide. Just as the Moon's gravity creates tides in Earth's oceans, the combined gravitational pull of all the mass in the Milky Way, hundreds of billions of stars, vast clouds of gas and dust, dark matter distributed through the galactic disk, exerts a tidal force on every object in the outer solar system. This galactic tide is not strong by any local measure. Close to the Sun, it is completely overwhelmed by solar gravity and means nothing. But at 50,000 or 100,000 AU, where the Sun's grip is already faint, the galactic tide becomes meaningful. It does not send one comet. it stirs the entire outer Oort cloud on a slow, continuous basis, like a vast spoon moving through a nearly still liquid. Over hundreds of millions of years, the galactic tide reshapes orbits, shifts populations of objects, and maintains a steady delivery of long-period comets into the inner solar system. Some researchers have suggested that this delivery rate may not be perfectly constant. As the solar system moves through the galaxy, it periodically passes closer to the denser regions of the galactic plane, where the galactic tide is stronger. These passages might temporarily increase the rate at which outer Oort cloud objects are disturbed and sent inward. The timing of these galactic plane crossings is a matter of ongoing study, and the connection to any historical patterns in comet delivery remains speculative, but the mechanism is real. The Oort cloud is not a passive, unchanging reservoir at the edge of space. It is a dynamic structure in constant, slow conversation with the galaxy that surrounds it. The comets it sends us are not random. They are the result of forces that stretch from the nearest star to the full disk of the Milky Way. There is a question this path has been circling without fully answering. Where does the Sun's gravity actually stop? It is not a simple question. Gravity does not have an off switch. The Sun's gravitational pull extends, in principle, forever, growing weaker with distance, but never reaching exactly zero. So the question is not where gravity stops, but where it stops being the dominant force. Where is the distance beyond which the Sun's pull is weaker than every other gravitational influence combined? That distance has a name. It is called the Hill sphere. The Hill sphere is the region surrounding the Sun within which the Sun's gravity is stronger than the competing gravitational pulls of the rest of the galaxy. Think of it as a tug of war. On one side is the Sun, pulling every object in its vicinity toward itself. On the other side is everything else, the nearest stars, the mass of the galactic disk, the distributed gravity of the Milky Way. The Hill sphere is the boundary where those two sides are equally matched. Inside it, the Sun wins. Outside it, the Sun loses. This concept is not unique to the Sun. Every massive body has a Hill sphere. The Earth has one. The Moon orbits within Earth's Hill sphere, which is why it stays with Earth rather than being captured by the Sun. Jupiter's Hill sphere is large enough to hold dozens of moons, and the Sun's Hill sphere is enormous. Current estimates place the Sun's Hill sphere at somewhere between 125,000 and 230,000 AU from the Sun. The uncertainty in that range reflects the difficulty of calculating exactly how the galactic environment's gravity is distributed. But even the lower estimate is vast. To put that in perspective, light travels from the Sun to Earth in about 8 minutes. Light travels from the Sun to the inner edge of the Oort cloud in roughly 13 months. Light travels from the Sun to the outer edge of the Hill sphere in approximately 2 years. The Sun's gravitational territory, defined by where it remains the dominant gravitational influence, has a radius of nearly 2 light-years. The nearest star, Proxima Centauri, is 4.2 light-years away. This means the gravitational spheres of the Sun and its nearest neighbours are not separated by vast empty voids. They are separated by a gap that is, in astronomical terms, not particularly large. The Hill sphere of the Sun and the gravitational territory of Proxima Centauri are separated by only about 2 light-years. In the future, billions of years from now, as the Sun moves through the galaxy, it is possible that passing stars could temporarily bring their Hill spheres into partial overlap with the Sun's. When that happens, objects near the outer boundary of the Oort cloud could be captured by the passing star, or objects from the passing star's cloud could be captured by the Sun. The Oort cloud is not just the edge of the solar system, It is the edge of where the sun is in charge, and that edge is surprisingly close to the territory of our stellar neighbours. In September 1977, 2 spacecraft were launched from Cape Canaveral within weeks of each other, Voyager 1 and Voyager 2. Their mission was to take advantage of a rare planetary alignment that would allow them to visit the outer planets in sequence, using each planet's gravity to slingshot the spacecraft onward to the next. Jupiter, Saturn, and in Voyager 2's case, Uranus and Neptune as well. Both spacecraft completed their planetary missions. And then, instead of slowing or being captured, they kept going. They are still going now. As of mid-2025, Voyager 1 is approximately 163 AU from the Sun, making it the most distant human-made object in history. Its radio signal, travelling at the speed of light, takes roughly 22 hours to reach Earth. On board, a set of instruments powered by decaying plutonium still returns data. The power supply is fading. Some instruments have already been turned off to conserve energy. At some point in the coming years, perhaps a decade or so, there will not be enough power to transmit anything. But the spacecraft itself will continue. Long after the last signal, long after any possibility of contact, Voyager 1 will keep moving outward through the darkness, a small golden object carrying a record of human sounds and images, crossing a distance no human voice will ever cover in real time. Most people associate Voyager with leaving the solar system, and in one meaningful sense it has. In 2012, after 35 years of travel, Voyager 1 crossed the heliopause, the boundary where the solar wind, the constant stream of charged particles flowing outward from the Sun, finally becomes too weak to push back against the interstellar medium. The heliopause sits at roughly 120 AU. Beyond it, Voyager entered a region dominated by interstellar particles and magnetic fields rather than solar ones. That crossing was real. It was significant. It marked the edge of the Sun's atmospheric bubble. But it was not the edge of the solar system. The heliopause at 120 AU is a particle boundary, the edge of the Sun's wind. The Oort cloud begins at 2000 AU. The Hill sphere extends to 200,000 AU. Voyager crossed the atmospheric edge of the solar system by the gravitational definition, by the definition of where the Sun still controls objects in stable orbits. Voyager has barely begun. Here is the number that makes this concrete. At Voyager's current speed of roughly 17 kilometers per second, the fastest sustained speed any human-made object has ever reached, reaching the inner edge of the Oort cloud, would take approximately 300 years. Reaching the outer edge would take roughly 30,000 years. Crossing the full Hill sphere would take on the order of 150,000 years. 300 years ago, the steam engine did not exist. The United States did not exist as a nation. The concept of a spacecraft was centuries away from being imagined. The probe that represents the furthest reach of human investigation is, by the gravitational measure, about 1/17 of the way to the Oort cloud. It is still, by every meaningful definition of the word, inside the solar system. It will remain inside it for thousands of years. There is one more thing worth saying about Voyager before this expedition moves deeper outward. The Voyager spacecraft are significant not only for where they are, but for what they are. They were designed in the 1970s, when computers were room-sized machines that occupied entire floors of buildings, when the concept of a laptop was decades away, when the internet did not exist, when every calculation of trajectory and every image processing step required either human arithmetic or machines operating at a fraction of the speed of any device you carry in your pocket today. The spacecraft themselves are the size of a small car. They carry instruments whose original design teams are mostly no longer alive. Their onboard computers operate with a processing power smaller than a modern digital wristwatch. Their radio transmitters, which must send signals across 22 light hours of space to reach Earth, operate at a power level of about 22 watts, roughly equivalent to a dim decorative light bulb. And they still work. Both Voyager spacecraft continue to transmit data. Scientists continue to receive it, analyze it, publish papers based on it. The tiny amount of power generated by their decaying plutonium fuel continues to decline, and in the coming years, one instrument after another will be shut down to conserve what remains. Sometime in the late 2020s or early 2030s, the power will not be enough to run any instrument at all. When that day comes, the spacecraft will continue. The signal will stop, but the object will not. Voyager 1, now moving at roughly 17 kilometers per second relative to the Sun, will continue outward through the sparse interstellar medium, carrying its golden record of Earth sounds and images on a path that will not bring it near another star for tens of thousands of years. Long after civilization has changed in ways impossible to predict, long after the technology that built Voyager has been superseded by things we cannot imagine, the spacecraft will be out there. Moving silent, somewhere in the space between the heliopause and the inner Oort cloud. Still inside the solar system by every gravitational measure, still 1/17th of the way to the Oort cloud. Still, in every sense that physics cares about, home, no mission to the Oort cloud has been seriously developed, because no propulsion technology we can envision would make the trip practical within any human institutional timeline. This is not an engineering problem we expect to solve next century. It is a statement about distance at a scale that current physics offers no shortcut through. The Oort cloud is not our next destination. It may never be. The only things that have crossed that distance are the comets, and they took millions of years to do it. Every few years, sometimes more often, a comet appears in the inner solar system. Some are faint, visible only through telescopes, some are bright enough to see with the naked eye, trailing a luminous tail of gas and dust across the night sky. For most of human history, a comet's appearance was a source of wonder or dread, an interruption of the ordered sky, an omen from somewhere beyond understanding. Understanding has since arrived, but it has not diminished the strangeness. A long-period comet is an object that has spent virtually its entire existence in the Oort cloud, frozen, dark, orbiting at enormous distance from the Sun. Then something disturbs it. A passing star, the galactic tide, a slow accumulation of gravitational nudges over millions of years. Its orbit shifts slightly, and its closest approach to the Sun drops from tens of thousands of AU to something far closer, and the comet begins to fall. The fall inward takes an extraordinary amount of time. For a comet coming from the outer Oort cloud, the infall alone can take millions of years. For most of that transit, the comet is in complete darkness. There is no sunlight to speak of at those distances, nothing to heat it, nothing to activate the volatiles frozen in its surface. It is just a frozen object moving through darkness, imperceptibly slowly from any human perspective, accelerating gradually as the Sun's gravity grows stronger. Eventually, after that unimaginably long transit, the comet enters the inner solar system. And everything changes. As it approaches the Sun, the frozen surface begins to sublimate. Ice turns directly to gas without passing through a liquid phase, because there is no atmospheric pressure to allow liquid to exist. That gas, carrying dust and tiny particles with it, forms the coma, the fuzzy atmosphere surrounding the comet's nucleus. The solar wind then pushes this material outward into the tail, always pointing away from the sun, which is why a comet's tail leads it on the way in and follows it on the way out. The brightness we see when a comet passes through the inner solar system is the light of an object reacting to the sun for the first time, or for the first time in millions of years. Some long-period comets are on orbits so elongated that they will never return. They pass through once, are deflected by the sun's gravity onto a hyperbolic path, and then travel outward forever. They are not just rare visitors, they are one-time travelers passing through on their way out of the solar system entirely. Comet Hale-Bopp, one of the brightest comets of the 20th century, is estimated to have an orbital period of several thousand years for its next return, shorter than its previous period because it was gravitationally altered by its last passage through the inner solar system. Before that, it may have spent tens of thousands of years travelling inward from the Oort cloud. When Hale-Bopp was last near the Sun, the Egyptian pyramids had not yet been built. There is another category worth noting because it opens a different kind of question. In 2017, an object called Oumuamua was detected passing through the inner solar system on a hyperbolic trajectory. Its origin was not the Oort cloud. Its trajectory traced back to interstellar space, to somewhere outside the solar system entirely. In 2019, a comet called Borisov arrived on a similar trajectory, also clearly interstellar in origin. These objects were visitors from another star system, passing through the solar system the way a comet from our own Oort cloud passes through another star's system. If our Oort cloud sends comets outward, it stands to reason that other stars' clouds do the same. The space between stars may carry a slow, sparse traffic of ancient icy objects, each one an ambassador from a distant solar system, passing through and continuing on. The Oort cloud is cold, extraordinarily cold. At 100,000 AU from the Sun, temperatures approach just a few degrees above absolute zero, the theoretical minimum temperature that physics allows. At those temperatures, chemistry effectively stops. Reactions that take seconds near the Sun would take billions of years at the outer Oort cloud. This near-total chemical stillness is the reason the Oort cloud contains the solar system's oldest unaltered material. When the solar system formed 4.6 billion years ago, it began as a vast rotating cloud of gas and dust. Gravity pulled the center of that cloud into the proto-sun. The surrounding material flattened into a disk, and within that disk, small solid particles began to stick together, first through simple contact and static electricity, then through gravity, building up into planetesimals, the building blocks of planets. Some of those planetesimals fell inward and became part of the rocky inner planets. Some became part of the giant planets. Some ended up in the asteroid belt. And some, through gravitational interactions with the forming giant planets, particularly Jupiter and Saturn, were scattered outward, thrown into highly elongated orbits that took them first into the outer regions of the solar system, and then, as those orbits were gradually rounded by passing stars and the galactic tide over billions of years, into the spherical shell that would become the Oort cloud. Those scattered objects carried with them the original chemistry of the early solar disk, the same raw materials that were present before the Earth had formed, before any planet had taken shape, and at the temperatures of the outer Oort cloud, that chemistry has been preserved almost perfectly ever since. The organic molecules detected in comets when they pass through the inner solar system include amino acid precursors, complex carbon compounds, and chemical structures similar to those found in interstellar molecular clouds, clouds of gas and dust in the galaxy that predate the formation of any star. Some of the chemistry in Oort cloud comets may be older than the solar system itself, inherited from the interstellar cloud from which the Sun formed. When a comet passes near the Sun and its frozen surface sublimates, releasing gas and dust into space, some of that material is being exposed to significant heat for the first time since before the Earth existed. The comet is, in a literal sense, a time capsule. Not a metaphorical one. A physical container of original chemistry preserved by cold and distance for 4.5 billion years. If we could ever retrieve an unaltered sample from the outer Oort cloud, from an object that has never been near the Sun, we would be holding the solar system's earliest known ingredients. We would be holding material that predates every continent, every ocean, every living thing that has ever existed on Earth. The story of how those original ingredients ended up in the Oort cloud requires briefly revisiting the most chaotic period in the solar system's history. For roughly the first 100 million years after the Sun formed, the solar system was not the orderly arrangement we know today. The giant planets were larger relative to the surrounding disk of material. Their orbital positions were different from where they are now. Jupiter's early position and mass meant that it had enormous gravitational influence over the surrounding material, scattering objects inward and outward with an efficiency that smaller planets could not match. Computer simulations of early solar system dynamics, particularly a set of models developed in the early 2000s and refined since then, suggest that the giant planets did not form in their current orbital positions. In the leading models, the giant planets migrated significantly in the first few 100 million years, shifting positions as they exchanged angular momentum with the disk of smaller bodies surrounding them. This migration had violent consequences. Objects were scattered outward by Jupiter and Saturn, some ejected from the solar system entirely, some sent into the long-period orbits that became the Oort cloud. During this period, the inner solar system also underwent significant bombardment. The surfaces of the Moon and Mercury, which are geologically quiet enough to have preserved their ancient impact scars, record a dense history of impacts in their oldest terrains. The period from about 4.1 to 3.8 billion years ago has been described as a time of heavy bombardment, during which many large impacts occurred on the terrestrial planets. The material responsible for those impacts likely came from the disrupted outer solar system, objects scattered inward by the migration and gravitational upheaval of the giant planets. The same events that produced the heavy bombardment also populated the Oort cloud. The objects scattered outward by Jupiter and Saturn during this period became the reservoir that Jan Oort inferred from comet data 4.6 billion years later. This means the Oort cloud and the ancient cratered surfaces of the Moon and Mercury are connected by the same history. The impactors that struck the early Earth and Moon were the inward scattered siblings of the objects that became the Oort cloud. The Oort cloud is, in this sense, the outward scattered fraction of the same population that shaped the early surfaces of the inner solar system. Some of the material in the Oort cloud may also have come from other forming solar systems. If the Sun formed in a stellar cluster, as many Sun-like stars do, then for the first few 100 million years it was surrounded by other young stars at relatively close distances. Those young stars were also forming their own protoplanetary disks and scattering their own debris outward. In a dense stellar cluster, gravitational interactions between young solar systems can exchange material. Some fraction of the objects in the early Oort cloud may have originated in other stellar nurseries, captured by the young Sun as the cluster gradually dispersed. If that is true, then the Oort cloud is not a purely solar record. It is a mixed record, containing both material that formed in the solar disk and material from the wider stellar environment in which the Sun was born. Distinguishing between these two populations, determining which Oort cloud objects are native and which might be interstellar captures, is a scientific challenge that current missions and instruments cannot yet meet. The answer is out there, frozen, orbiting 2000 AU from the nearest instrument capable of reading it. We cannot do that yet. We cannot get there. But the chemistry comes to us, carried in on a falling comet, arriving in our sky after 1 million years in transit. The solar system has never been fully explored, by any measure. We have visited the Moon, we have sent landers to Mars, we have flown spacecraft past all 8 planets, we have sent a probe to the surface of an asteroid and another to land on a comet. We have crossed the heliopause, we have photographed Pluto and Arrokoth and a handful of Kuiper Belt objects. But no mission has ever been sent to the Oort cloud. No mission is currently being planned for the Oort cloud. No mission in any serious stage of development would reach the Oort cloud within a human lifetime, or within several human lifetimes. This is worth sitting with, because the Oort cloud is not a theoretical curiosity. It is a real structure containing an estimated 100 billion to 2 trillion objects surrounding the entire solar system in a spherical shell. It preserves the oldest material in the solar system. It is the source of long-period comets. It defines the true gravitational extent of the Sun's territory. By almost any scientific measure, it is one of the most significant structures in the solar system. And we have never been there. New Horizons, which reached Pluto in 2015 and is now the most remote active spacecraft after the Voyagers, travels at roughly 14 kilometers per second. At that speed, it would take approximately 485 years to reach the inner edge of the Oort cloud. No one designing a mission today can commit to a 485-year travel time. Even if such a commitment were made, the spacecraft would arrive in the mid-26th century using technology designed in the early 21st, communicating across a distance so large that signals would take years to return. Mission planning at that scale requires certainty about institutions, funding, technology, and political continuity across dozens of generations. We do not plan on those timescales. We never have. There are scientists who study advanced propulsion concepts, solar sails, laser propulsion, nuclear pulse propulsion, theoretical drives that could increase speeds by an order of magnitude or more. Some of these concepts, if ever fully developed, could reduce the travel time to the inner Oort cloud from centuries to decades. A mission with a 50-year travel time is at least conceptually within the range of human institutional commitment, the way a 50-year satellite program is. But none of those technologies exist in operational form, and even a mission that reached the inner Oort cloud would still be nowhere near the outer Oort cloud or the Hill sphere boundary. The honest statement is this: for the foreseeable future, our understanding of the Oort cloud will come entirely from the comets it sends us, from telescopic observations of distant Oort cloud candidates, and from models. The structure itself will remain physically unvisited, and yet the comets keep arriving. One of the most scientifically significant structures in the solar system continues to introduce itself. One frozen messenger at a time, across a distance nothing we have built can currently cross. Everything in the Oort cloud has a future, and so does the Oort cloud itself. It is easy to imagine the Oort cloud as static, a fixed shell at the edge of the solar system that has always been there and will always remain. But the Oort cloud is losing material continuously. Every comet that falls inward is, in a sense, a withdrawal from the outer solar system's account. Some of those comets, after passing through the inner solar system, are ejected entirely. Their orbits altered by a close approach to Jupiter or another giant planet, until their velocity exceeds escape velocity, and they leave the solar system forever. Some strike a planet or the sun itself. Some are gradually ground down through repeated passages, losing material each time until they become inert dark rocks with no remaining volatiles. Comets are not returned to the Oort cloud. When they leave, they are gone. At the same time, passing stars and the galactic tide do not only send objects inward, they also send some objects outward, past the Hill sphere and into true interstellar space. An Oort cloud object, sitting near the outer boundary, held by the sun's gravity, with the barest possible grip, can be permanently removed by a single gravitational encounter with a passing star. Over billions of years, this process has already removed a significant fraction of the original Oort cloud population. Current models suggest the Oort cloud we see today may contain substantially fewer objects than it did early in the solar system's history. The original population, assembled in the first hundreds of millions of years of solar system formation, was likely much larger. What remains is a depleted version of the original cloud, still enormous by any human measure, but thinned by billions of years of cometary delivery and stellar perturbation. This depletion will continue, very slowly, across timescales that dwarf the current age of the universe many times over. The Oort cloud will thin further. And then, there is the Sun's own future. In roughly 5 billion years, the Sun will exhaust its core hydrogen fuel and begin to expand into a red giant, swelling outward until it likely engulfs Mercury and possibly Venus and Earth. The inner solar system will be transformed beyond recognition, but the Oort cloud, at distances of thousands to hundreds of thousands of AU, will be almost entirely unaffected by the Sun's expansion. The objects there are too far away to care what state the Sun's surface is in. When the Sun eventually collapses into a white dwarf, a dense, cooling remnant roughly the size of the Earth, but with about half the Sun's current mass, it will retain a gravitational field. That field will be weaker than the Sun's current one, and its Hill sphere will shrink accordingly. Some outer Oort cloud objects will be lost as the gravitational boundary contracts, but the inner and middle regions of the Oort cloud will remain, orbiting a cooling white dwarf star in complete darkness. The Oort cloud will outlive the Sun as a living star. In the very long future, billions or trillions of years from now, the white dwarf will cool and fade, eventually becoming a dark object invisible against the night sky. The Oort cloud objects will continue orbiting it, slowly, frozen, undisturbed, in a darkness complete enough that no light from any source would be detectable. The last gravitational remnant of the solar system may be the Oort cloud, still weakly orbiting a cold, dark star. Long after everything inside Neptune's orbit has been consumed, transformed, or scattered, this expedition has been building toward one question, the same question that was in the title at the beginning. Where does the solar system actually end? Now, with everything we have covered, the honest answer is, it depends on what you are measuring, and each definition, each way of drawing the line, reveals something true about a different aspect of what the solar system is. The first definition is atmospheric. The heliosphere is the bubble of solar wind that surrounds the Sun and extends outward in all directions. Where that wind loses its dominance against the interstellar medium, the heliopause marks the outer boundary of the Sun's atmospheric influence. That boundary sits at roughly 120 AU. Voyager 1 crossed it in 2012. By this definition, the solar system ends at 120 AU, and Voyager is outside it. That is a real boundary. It is physically meaningful. But it is the shallowest of the three. The second definition is structural. The Sun's gravitational territory is populated with objects, from the inner planets to the asteroid belt to the Kuiper Belt to the scattered disk to the Oort cloud. The furthest objects in that population, orbiting at the outer edge of the Oort cloud, are at somewhere between 50,000 and 200,000 AU. By this definition, the solar system ends where the last Sun-orbiting objects orbit, which is somewhere in that range. This is the definition most consistent with the ordinary meaning of the word. The solar system is the collection of things that orbit the Sun. By that measure, the outer Oort cloud is still fully inside the solar system. The third definition is gravitational. The Hill sphere marks where the Sun's gravity is no longer the dominant force in the local environment, where the combined pull of the rest of the galaxy becomes stronger than the Sun's individual pull. That boundary sits at approximately 125 to 230,000 AU. Beyond it, nothing can orbit the Sun in a stable long-term orbit. Beyond it, you are gravitationally speaking, not in the solar system. 3 definitions, 3 boundaries, 3 ways of measuring where the solar system ends. 120 AU, 100,000 to 200,000 AU, 125,000 to 230,000 AU. The smallest of those numbers is where Voyager has travelled. The largest is nearly 2,000 times further than that. If you use the gravitational definition, the solar system is a sphere roughly 2 light-years in radius, nearly a third of the way to the nearest star. By that measure, we do not live in a small planetary neighbourhood with a thin outer ring. We live at the centre of a gravitational structure so large that it fills a substantial fraction of the space between us and our nearest stellar neighbour. The familiar image of the solar system, the Sun and 8 planets and a distant ring of ice, describes not even 2% of the solar system's true gravitational radius. The solar system does not end at the last planet. It does not end at Pluto. It does not end where Voyager is. It ends somewhere we have never been, somewhere we may never go, in a region so cold and dark and remote that the only things that have ever crossed it are ancient icy objects travelling on million-year trajectories, falling toward a sun they have not been close to since the solar system was young. Step outside on a clear night and look up. The stars you see are close ones, by cosmic standards. The nearest is 4.2 light-years away. Most of the ones you can see with the naked eye are within a few hundred light-years. The Milky Way behind them spans roughly 100,000 light-years across. And the solar system, the gravitational territory of the single star you orbit, extends almost 2 light-years in every direction from the point where you are standing. Somewhere out there, in the darkness beyond any instrument we have ever built, trillions of frozen objects are completing orbits that take tens of thousands of years to finish. Most of them have never been near the Sun. Some of them formed before the Earth existed. They carry chemistry from the original cloud of gas and dust that became this solar system, preserved at temperatures near absolute zero for 4.6 billion years. Every comet you have ever seen in the sky, every bright streak of light that has crossed the night over any human civilization in recorded history, was one of those objects completing its inward fall, falling toward the Sun for 1 million years or more, arriving briefly in the inner solar system, and then either returning outward or continuing into interstellar space forever. We did not understand where those comets came from for most of human history. We named them omens. We recorded their appearances as warnings. We watched them with wonder and unease. We understand them better now. They come from the edge of the solar system. They come from a place no human has ever visited, that no mission has ever reached, that will not be explored in any lifetime we can currently imagine. The solar system is not the small familiar neighbourhood of 8 planets circling a star. It is a gravitational sphere nearly 2 light years across, containing trillions of objects. Most of them never touched by significant sunlight, orbiting in silence at distances that reduce the sun itself to just another point of light in the sky. The edge of that sphere is not a wall, it is a gradient, a slow, cold fading of the sun's influence into the wider pull of the galaxy. There is no moment when you cross from inside to outside. There is only the sun growing dimmer and its gravity growing weaker, until at some vast distance, the galaxy itself holds more sway over what moves through that space than the star at the centre of it. That is where the solar system ends. Not at Neptune, not at Pluto, not where Voyager is now. Out there, in the dark, at a distance light takes a year to cross. The comets keep their secrets well. When a long-period comet finally enters the inner solar system after its million-year transit, it carries on its surface and in its interior something that planetary scientists have been trying to read carefully for decades. Not the ice, which sublimates away almost immediately as the comet warms. Not the dust, which trails behind in a long luminous tail, but the chemistry embedded in both, the molecular fingerprints of a time before this planet existed. The organic molecules detected in comets are not exotic. They include water ice, carbon monoxide, carbon dioxide, methane, ammonia, and more complex compounds including formaldehyde, methanol, and glycine, one of the simplest amino acids and a building block of proteins. These are not the molecules of life itself, but they are many of the ingredients from which life's chemistry is assembled. The significance of finding them in comets is not that comets brought life to Earth. That claim goes well beyond current evidence. The significance is what those molecules tell us about where they came from. The chemistry of Oort cloud comets is consistent with the chemistry found in the cold molecular clouds of interstellar space, vast regions of gas and dust in the galaxy where temperatures are so low that complex organic molecules can form and persist on the surfaces of dust grains. These clouds are the raw material from which stars and solar systems form. When a cloud collapses under gravity and begins to form a new star, the chemistry of the cloud goes along for the ride, embedded in the planetesimals that scatter outward into the forming system's Oort cloud. Some of the molecules in Oort cloud comets may therefore predate the solar system. They may have been assembled in interstellar space before the sun ever ignited, preserved first in the cold of an interstellar cloud, then in the cold of the forming Oort cloud, and finally delivered to the inner solar system on a comet's path billions of years after their formation. There is something arresting about that sequence. A molecule assembled in an interstellar cloud before the Earth existed, preserved through the formation of the solar system, orbiting undisturbed in the Oort cloud for 4.6 billion years, and then delivered into the inner solar system on a comet that crosses our sky. Chemistry that is older than any rock on Earth, arriving from the farthest edge of the solar system, briefly passing close enough to study. We have collected some of this material. The Stardust mission returned cometary dust samples from Comet Wild 2 in 2006. The Rosetta mission orbited and landed on Comet 67P/Churyumov-Gerasimenko between 2014 and 2016, analysing its surface and coma chemistry in extraordinary detail. Wild 2 and 67P are short-period comets, not Oort cloud objects, and their chemistry may be somewhat different, but they gave us a methodology, a proof of concept that comet chemistry can be studied in detail. The Oort cloud comets are the ones we cannot yet reach, the pristine objects that have never been near the sun at all. If we could ever retrieve material from one of those, from an object that has spent its entire existence in the outer Oort cloud, untouched by solar heating, we would be holding the solar system's most complete original record. The archive exists, It is simply at a distance we cannot yet cross. The first time the Oort cloud became a formal scientific concept was in 1950. Jan Hendrik Oort was a Dutch astronomer, one of the most influential planetary scientists of the 20th century. He had already made major contributions to understanding the structure of the Milky Way, mapping the galaxy's rotation, and helping establish that the Sun orbits the galactic centre. In 1950, he turned his attention to a different problem. Where do comets come from? Oort analysed the orbital characteristics of 19 long-period comets whose orbits were well enough determined to be useful. He looked at a specific quantity, the orbital energy of each comet, which determines how tightly or loosely it is bound to the Sun. A comet with very low orbital energy, nearly zero, is only barely bound to the Sun, meaning it came from a very large distance and will take a very long time to return, if it returns at all. What Oort found was a clustering. Many of the long-period comets he analysed had orbital energies consistent with origins at distances between roughly 40,000 and 150,000 AU from the Sun. Far more of them had these very large origin distances than would be expected if comets were simply wandering inward from random locations. The distribution was not random, it was structured. He proposed that there must be a reservoir of comets at those distances, a spherical cloud surrounding the solar system, from which comets were occasionally perturbed inward by passing stars. And he proposed that the comets we see arriving in the inner solar system for what appears to be the first time are genuinely arriving from that cloud for the first time, their orbits disturbed after billions of years of stability. The proposal was bold. There was, and still is, no direct observational confirmation of the Oort cloud. No image of it exists. No spacecraft has visited it. Oort was making an inference from orbital data, working backward from the properties of arriving comets to deduce the existence of the structure that must be sending them. But the inference was clean, and it held up. As more comet orbits were measured over the following decades, the pattern Oort identified became clearer and more consistent. The dynamical models of how such a cloud would evolve over time matched the observations. The mechanisms, stellar perturbation, and the galactic tide, which were better understood in later decades, provided the physical explanation for how the cloud sends comets inward. The Oort cloud is now as well established a feature of the outer solar system as the Kuiper Belt, despite never having been directly imaged. It is inferred from evidence the way the interior of the Earth is inferred from seismic waves, or the way dark matter is inferred from galactic rotation curves. The inference is based on physical laws, is consistent across many independent observations, and has no equally satisfying alternative explanation. Jan Oort looked at the orbital paths of comets arriving in the inner solar system and deduced the existence of a spherical shell of frozen objects nearly 2 light-years away. He had no spacecraft to send there, no telescope powerful enough to see it, no instrument capable of detecting it directly. He had physics, geometry, and data. That was enough. The solar system began in violence. Not violence in the human sense, but in the physical sense of vast energies moving through enormous spaces in very short times. Roughly 4.6 billion years ago, a region of an interstellar molecular cloud, perhaps disturbed by the shockwave of a nearby supernova, began to collapse under its own gravity. As it collapsed, it rotated faster, a consequence of conserving angular momentum the way a spinning skater speeds up by pulling their arms inward. The centre of the collapsing cloud became dense and hot enough to ignite nuclear fusion, and a star was born. Around that star, the remaining material settled into a disk, the solar nebula. Within that disk, temperature gradients created zones. Close to the young sun, only rocky and metallic materials could condense, because temperatures were too high for ices. Further out, beyond what planetary scientists call the frost line, temperatures were low enough for water ice and other volatile ices to exist in solid form. In those outer regions, solid particles were more abundant, allowing larger planetesimals to form faster. Jupiter formed first among the giant planets, growing so large so quickly that its gravity began to dominate the outer solar system. Saturn, Uranus and Neptune followed, and as these giants grew, they began to disturb the orbits of the smaller bodies around them, scattering them outward or inward, reorganizing the solar system's architecture. Some of the icy bodies in the outer solar nebula were ejected inward, where they were absorbed by the forming inner planets or fell into the Sun. Many were ejected outward, sent onto highly elongated orbits that took them far from the planetary region. Over time, as those elongated orbits were gradually circularized by the galactic tide and passing stars, the scattered objects settled into what would become the Oort cloud. This process happened early in the solar system's history, in the first few 100 million years. Most of the Oort cloud's population was established during this period. The objects that ended up in the outer Oort cloud had been thrown outward by gravitational encounters with the giant planets, particularly Jupiter, which is massive enough to eject objects to Oort cloud distances efficiently. This formation story has an important implication. The objects in the Oort cloud are not random debris from the outer galaxy. They are solar system material, formed from the same disk that formed the planets, carrying the same original chemistry. They are siblings of the material that became Earth, Mars, Jupiter's moons, and the Kuiper Belt. The difference is only that they were ejected outward instead of accreted inward. Some models of early solar system evolution suggest the solar system may have originally formed close to other young stars, as part of a stellar cluster. If so, the early Oort cloud may have been shaped not only by the solar system's own giant planets, but by the gravitational influence of nearby young stars before the cluster dispersed. Some fraction of the Oort cloud may even include objects captured from other forming solar systems in that early cluster environment. The Oort cloud is the solar system's most ancient suburb. It was built from the original construction materials, populated during the solar system's most chaotic early phase, and has been sitting in the dark ever since, while the planets settled into their current orbits and life eventually appeared on the third one inward. It is worth asking, with complete honesty, why any of this matters. The Oort cloud has never been visited. Its objects have never been landed on, sampled, or closely photographed. The comets it sends us have been studied, but the Oort cloud itself remains beyond any instrument we have. It will not be explored in any human lifetime currently alive, and possibly not in any human lifetime for centuries to come. So why spend time understanding it? One answer is practical. Long-period comets originating from the Oort cloud represent a real, if statistically small, category of potential impactors for the inner solar system. Unlike asteroids in the main belt, which have been systematically catalogued for decades and whose orbits are increasingly well known, Oort cloud comets arrive with very little warning. A new long-period comet on a sunward trajectory might be detected months to a few years before closest approach, compared to the decades of advance notice we now have for most known near-Earth asteroids. Understanding the Oort cloud's population, its distribution and the frequency with which passing stars and the galactic tide disturb it, is therefore relevant to understanding the background rate of long-period comet deliveries to the inner solar system. That background rate is part of the full picture of impact risk. But the deeper answer is not about risk. It is about understanding what the solar system actually is. The picture most people carry of the solar system is a picture of the inner 8% at most of its gravitational radius. the mental model of the solar system as a collection of planets. With a bit of asteroid belt and a faint ring of Kuiper Belt objects at the edge, is a description of the most densely packed inner region of a structure that extends almost 1,000 times further in every direction. Knowing the true extent of the solar system changes what it means to say that something is in it or outside it. Voyager is inside the solar system. It will remain inside the solar system for longer than human civilization has existed. The idea that Voyager has left the solar system, while meaningful in the atmospheric sense, is profoundly incomplete in the gravitational sense. Knowing the true extent of the solar system also changes the scale of what interstellar travel would require. When people discuss the challenge of reaching another star, the challenge is typically framed as crossing the roughly 4.2 light-years to Proxima Centauri. But leaving the solar system, leaving it in the gravitational sense, would require crossing a distance approaching 1 to 2 light-years just to reach the Hill sphere boundary. An interstellar mission does not begin when the rocket launches. It begins when the spacecraft finally clears the solar system's outermost gravitational territory. And knowing the true extent of the solar system places us in a different relationship with the comets we see. They are not visitors from somewhere vaguely distant. They are residents of the same solar system, objects that were thrown outward at the beginning of the solar system's history and have been orbiting ever since, returning to the inner region after journeys that began before recorded human civilization, before the construction of any monument still standing, before the development of written language. The solar system is not small. The solar system is not well explored. The solar system is not a solved problem. It is a structure we have barely begun to understand, extending in all directions to a boundary nearly 2 light-years from the star at its centre, containing trillions of objects we have never visited, preserving chemistry older than the Earth, sending us comet messengers on million-year transits, and sitting in quiet gravitational conversation with the galaxy around it. The comets that fall inward from the Oort cloud do not arrive alone in history. They arrive in a sky already full of human interpretation. For most of recorded civilization, a comet was not an astronomical object with an orbital period and a chemistry and an origin story. It was a break in the expected order of the sky. The sky was supposed to be predictable. The stars rose and set on schedule. The planets moved in patterns that careful observers could learn to anticipate. The sun and moon followed their cycles. Order was the rule of the heavens. A comet violated that order. It appeared without warning, moved through the constellations on its own trajectory, brightened and then faded over weeks or months, and disappeared. The ancients had no framework for it. A bright comet arriving over a period of geopolitical tension became an omen of war. A comet that appeared before the death of a ruler was interpreted as a herald of that death, or in retrospect the cause of it. Julius Caesar's assassination was followed by a comet that the Romans interpreted as his soul ascending to the heavens. Halley's comet appeared over England in 1066, and its appearance was depicted in the Bayeux embroidery alongside the events of the Norman conquest. The interpretations were wrong, of course, but the sense of significance was not entirely misplaced. A comet is genuinely unusual. Its appearance in the sky does represent something arriving from elsewhere, from far beyond the normal range of human observation, from a region no eye has ever seen and no hand has ever touched. The ancients lacked the framework to understand what that meant physically, but they were not wrong to feel that a comet was a kind of messenger. It is. It is simply a messenger from further away than they imagined. The first person to understand comets as physical objects travelling on predictable orbits was Edmund Halley in the early 18th century. Halley recognised that comets recorded in 1531, 1607 and 1682 were the same object returning on a roughly 75-year orbit. He predicted its return in 1758, which occurred after his death. That return was one of the first successful quantitative predictions in the history of astronomy, a demonstration that the heavens operated by laws that could be calculated and applied. Halley's Comet is a short-period comet, meaning it comes from within the inner solar system's history, likely originally a Kuiper Belt or scattered disk object that was deflected inward. It is not an Oort cloud object. But the principle Halley demonstrated, that comets move by physics and not by omen, was the foundation on which Jan Oort built his 1950 analysis. From Halley's calculation to Oort's cloud. From an omen to an archive. From a sign in the sky to a piece of the solar system's outermost structure, falling inward from a distance that light takes more than a year to cross. That arc of understanding, from fear to physics, from mystery to measurement, is one of the better stories science has to tell about how human beings relate to the sky. The distances involved in this story are genuinely difficult for the human mind to hold. Not because we lack intelligence, but because our minds evolved to navigate distances measured in meters and kilometers, not in light years and tens of thousands of astronomical units. Scale at this level requires deliberate effort to feel, and even then it tends to slip away. Here is one more attempt to make it land. The solar system, as most people imagine it, the 8 planets and their moons and the asteroid belt, fits within a radius of about 40 AU. If you were to shrink the solar system to the size of a football pitch, the Sun would be at the centre and Neptune would be at one edge of the pitch. On that same scale, where would the inner edge of the Oort cloud be? The inner Oort cloud would begin about 2.7 kilometres away, not at the edge of the pitch, nearly 3 kilometres from the pitch, down the road, past whatever building is in the way. The outer Oort cloud, at 100,000 AU, would be about 67 kilometres away from the football pitch that represents the planetary solar system. The hill-sphere boundary would be at roughly 130 to 200 kilometres. The nearest star, Proxima Centauri, would be at about 280 kilometres on this scale. On a football pitch-sized solar system, the planetary region and the Oort cloud are not nearby structures. The Oort cloud's inner edge is 3 kilometres down the road. Its outer edge is 67 kilometres away. The nearest star is 280 kilometres away. The entire region most people call the solar system is the football pitch. The actual solar system, by gravitational extent, is a sphere 130 to 400 kilometres in radius. Nothing we have built has ever reached even the first 3 kilometres off that pitch. No probe, no mission, no spacecraft in history. The most travelled object humanity has ever built, Voyager 1, has made it roughly 200 metres from the edge of the pitch on this scale, just barely off the grass. That is where we are. That is the frontier we are actually exploring, not the full solar system, but the first few hundred metres of a structure that extends for hundreds of kilometres in every direction. The rest of it is out there, dark, cold, populated, and waiting. The outer Oort cloud is a place of extraordinary quietness, quiet in the sense of darkness. At 100,000 AU, the Sun provides about 100 billion times less light than it does at Earth's distance. On a scale where full sunlight at Earth is a bright day, the sunlight at the outer Oort cloud is not even comparable to the deepest astronomical night sky as seen from a mountaintop. It is darkness of a kind that human eyes would perceive as absolute, with the Sun visible as nothing more than the brightest single point in a sky full of stars. Quiet in the sense of temperature. Surface temperatures on objects in the outer Oort cloud approach a few Kelvin, just a few degrees above the absolute zero of thermodynamics. At these temperatures, nearly all chemistry stops. Molecules that would react in seconds at room temperature would take the age of the universe to interact at Oort cloud temperatures. The objects there are chemically frozen in time as surely as they are physically frozen, quiet in the sense of motion. The orbital speeds of objects in the outer Oort cloud are extraordinarily slow. Earth orbits the Sun at roughly 30 kilometers per second. Neptune orbits at about 5 kilometers per second. An object in the outer Oort cloud at 100,000 AU might orbit at less than 100 meters per second, a little faster than a sprint, covering ground so slowly that it takes tens of thousands of years to trace even a small arc of its orbital path. Quiet in the sense of density. The average distance between Oort cloud objects is enormous. Even with estimates of 1 trillion or more total objects, the average spacing between them is roughly tens of millions of kilometers, larger than the distance between Earth and the Moon many times over. The Oort cloud is not a dense cloud in any ordinary sense. It is a vast, sparse population of individual objects with enormous amounts of empty space between each one. If you are somehow transported to a random point within the outer Oort cloud, the most likely outcome is that you would see nothing nearby at all. No objects visible to the naked eye, no significant source of light. The Sun, one point of light among many in the sky, slightly brighter than the rest. Darkness in all directions. An occasional object, likely no larger than a few kilometers across, drifting at a vast distance, invisible. This is the edge of the solar system. This is what the outermost structure of our gravitational home looks like. Not dramatic, not dense, just vast, dark, cold, and almost impossibly empty by any human measure of emptiness. And yet it is there. And yet it is ours. And yet, every so often, one of its frozen inhabitants begins to fall. What would it take to actually explore the Oort cloud? Not in the distant theoretical future, not with technology we might imagine being invented centuries from now, but with technologies that could plausibly be developed within the next 50 to 100 years, the kind of time frame that connects to decisions being made today. The most serious proposals involve solar sail technology combined with laser propulsion. A light sail, a large reflective surface pushed by either sunlight or a directed laser beam, has no reaction mass to exhaust, and can in principle accelerate continuously over very long distances. The Breakthrough Starshot initiative has proposed laser-driven light sails capable of reaching a few percent of the speed of light for tiny probes aimed at other star systems. At 1% of the speed of light, which would require laser infrastructure far beyond anything currently built, a probe would travel roughly 3,000 kilometers per second. At that speed, it would reach the inner edge of the Oort cloud in approximately 3.6 years. That is an actually manageable time frame. The challenge is deceleration. A probe moving at 1% of the speed of light has enormous kinetic energy and no way to slow down unless it carries a deceleration system or has another laser array waiting at the destination to push it backward. Without deceleration, the probe flies through the Oort cloud in a fraction of a second of encounter time, too fast for any useful science. Slower probes avoid this problem but require longer travel times. A probe travelling at 200 kilometers per second, roughly 10 times faster than Voyager, would reach the inner Oort cloud in about 30 years. Slow enough to decelerate, fast enough to be a mission plannable within a human career span. 200 kilometers per second is roughly 100 times faster than Voyager's current speed. Current best propulsion concepts for near-future missions, including nuclear electric propulsion and solar electric propulsion with advanced power sources might achieve 50 to 100 kilometers per second over long mission durations. The gap between current capabilities and what an Oort cloud mission would require is real, but it is not infinite. No such mission is currently funded or formally proposed at any space agency. The scientific community has discussed it in workshops and concept studies, but the combination of cost, technical challenge, and institutional timescale has prevented it from becoming a funded priority. Other destinations, Mars, Europa, the outer planets, asteroids with return samples, have clearer short-term scientific payoffs and less extreme engineering requirements. The Oort cloud waits. It will keep waiting. It has been waiting for 4.6 billion years. A few more centuries will not change it. The trillions of frozen objects in the outer solar system will continue their slow orbits, undisturbed, preserving their ancient chemistry, occasionally sending a messenger inward, indifferent to whether anything in the inner solar system ever comes to look at them. But if we do go, if some generation in the coming centuries builds the propulsion systems and the funding mechanisms and the institutional will to send a probe outward past the heliopause, past the scattered disk, past the first 2000 AU of empty space to the inner edge of the Hills cloud, the scientific return would be extraordinary. A close-up view of a pristine Oort cloud object, a surface untouched by solar heating, chemistry preserved since before the Earth formed, a piece of the solar system's original construction material, finally examined at close range after 4.6 billion years of waiting in the dark. That is not a certain future. It may not even be a near future. But it is a possible one. Now all the tools are in place. The distances are mapped, the structures are named, the evidence is laid out. The question the title asked can be answered in full. Where does the solar system actually end? At 120 AU, the solar wind stops dominating the particle environment. The heliosphere ends. Beyond it is the heliosheath, and then the heliopause, where solar particles and interstellar particles reach a kind of rough equilibrium. Voyager 1 crossed this boundary in 2012, Voyager 2 crossed it in 2018. By this definition, both spacecraft are outside the solar system. This is a real and meaningful boundary. The Sun's atmospheric influence ends here. The charged particle environment changes. The magnetic field structure changes. In a physical, measurable sense, the solar wind stops being the dominant local force. But the Sun's gravitational influence does not stop here, not by a factor of thousands. At roughly 2000 AU, the inner edge of the Oort cloud begins. This is where the Sun's population of gravitationally bound objects extends beyond the scattered disk and begins the vast outer structure. Objects here have been orbiting the Sun for the full 4.6 billion years of the solar system's history. They are as much a part of the solar system as any comet or asteroid. The Oort cloud's outer population extends to somewhere between 50,000 and 200,000 AU, with most estimates placing the meaningful outer boundary around 100,000 AU. This is where objects are so loosely bound to the Sun that perturbations from passing stars and the galactic tide can alter or remove their orbits over millions of years. But even these objects are currently in orbit around the Sun. They are currently inside the solar system by any population-based definition. At roughly 125,000 to 230,000 AU, the Sun's helisphere ends. Beyond this distance, the Sun's gravity is weaker than the combined gravitational environment of the galaxy. Objects here cannot maintain stable long-term orbits around the Sun. This is the gravitational edge of the solar system, the boundary beyond which nothing can permanently belong to it. 3 boundaries. Each one measures something real. Each one gives a different answer to the same question. If you define the solar system as the region dominated by the sun's wind, it ends at 120 AU. If you define it as the region populated by objects in orbit around the sun, it ends somewhere between 50,000 and 200,000 AU. If you define it as the region gravitationally dominated by the sun, it ends at roughly 125 to 230,000 AU. The honest answer is that the solar system does not have one edge. It has gradients. It is a structure that fades rather than stops, whose influence in different physical domains ends at different distances, and whose true outer boundary, by the most physically meaningful definition, sits at a distance that makes the planetary region look like a small courtyard in front of a vast building. The solar system is not where you think it ends. It ends, if it ends anywhere, approximately 2 light years from where you are standing. One of the more philosophically interesting aspects of the Oort cloud is what it does to the concept of the solar system as a home. Most people think of the solar system as a place they are in, the way you are in a house or a city. The solar system is the neighbourhood. The sun is the centre. The planets are the rooms. Earth is the room we live in. It is a bounded, comprehensible space. But the Oort cloud extends that space to something that cannot be held in the mind as a bounded place at all. The solar system, by its gravitational definition, is not a neighbourhood. It is a gravitational domain nearly 2 light-years across. At that scale, the entire planetary region, the 8 planets, the asteroid belt, the Kuiper Belt, everything we have ever visited or photographed, is an infinitesimally small cluster at the centre of a sphere so large that it extends roughly halfway to the nearest other star. If you think of the solar system as a sphere 2 light-years in radius, and you think of the planetary region as a cluster at the centre with a radius of about 50 AU, then the ratio of the 2 volumes is roughly 1 trillion to 1. For every cubic AU of space in the planetary region, there are about 1 trillion cubic AU in the full gravitational solar system. Nearly all of that space is in the Oort cloud. The solar system's volume is almost entirely Oort cloud. Everything else, all the planets, all the missions, all the history of space missions, all the objects humanity has ever directly studied, occupies 1 part in 1 trillion of the solar system's actual volume. This is not a reason for despair. It is a reason for a different kind of perspective. The solar system we have explored is not a complete picture. It is a beginning. A tiny bright centre of a structure that extends through the darkness in all directions to a boundary nearly 2 light-years away. And that boundary is alive. Not biologically, but physically. It is stirred by passing stars. It is shaped by the galactic tide. It exchanges material with the wider galaxy through the interstellar visitors that pass through and through the comets that are eventually ejected. It is in continuous, slow exchange with the broader cosmic environment. The solar system is not a closed box. It is an open structure, connected to the galaxy by gravity and by the slow traffic of icy objects moving in all directions. Some of our Oort cloud comets will eventually be ejected and become interstellar objects. Some interstellar objects will be captured and become part of our Oort cloud. The boundary is real, but it is not impermeable. The solar system, fully understood, is not a neighbourhood. It is a region of gravitational dominance in a galaxy full of regions of gravitational dominance, each one connected to the others by the slow exchange of material across the light years between them. That is what the Oort cloud tells us about where we live. Step outside on a clear night and look up. The stars you can see with the naked eye are a local sample of the galaxy, most of them within a few hundred light-years. The nearest one, Proxima Centauri, is 4.2 light-years away. You cannot see it without a telescope. It is there nonetheless, a small red star moving slowly through its own gravitational neighbourhood, holding its own planetary system, sending its own solar wind outward in a heliosphere of its own. Between you and Proxima Centauri, there is a region of space that is not simply empty. The outer limits of the solar system extend roughly halfway toward that nearest neighbour. If you travelled from Earth directly toward Proxima Centauri and looked back when you had covered about a third of the distance, you would still be, technically, gravitationally, measurably, inside the solar system. That is the scale of the place you live in. Somewhere in the darkness out there, beyond every planet, beyond every mission, beyond every image ever taken, trillions of frozen objects orbit the Sun in silence. They have been orbiting for longer than the Earth has had complex life. Some of them carry molecules assembled in interstellar space before the solar system formed. Some of them have never been close to the Sun at all, and never will be. Some of them, disturbed by a passing star whose light we might be seeing in the night sky right now, have already begun a million-year fall inward that will eventually produce a comet some future civilization might watch across the sky. Every comet ever recorded by any human civilization was one of those objects completing that transit. When the ancient Babylonians recorded the appearance of a comet, when medieval astronomers charted its path, when people stood outside in modern times and watched a bright comet trail across the dark above them, they were watching an Oort cloud object completing a transit that began before their civilization existed. A frozen object from the outermost edge of the solar system, falling toward the Sun for 1,000,000 years, arriving briefly in the inner region, then continuing outward. We called them omens. We called them warnings. We called them signs. They were travellers. They came from the edge of home, which is a place much further away than most of us ever knew. The solar system does not end at the last planet. It does not end at Pluto. It does not end where Voyager is now. It ends out there, in the dark, at a distance that light takes a year to cross, in a region of frozen silence that belongs to the same sun that warms the ground you are standing on. That is where the solar system actually ends. The night sky over the observatory at Leiden, Netherlands in 1950 was unremarkable. The stars were out, the instruments were running. Jan Oort was working through comet orbital data the way an astronomer works through any careful analysis, methodically, without drama, converting numbers into understanding. The dataset was small by modern standards. Only a few dozen long-period comets with well-determined orbits were available to study. Computing the orbital parameters of a single comet, working backward from its observed positions to determine its path around the Sun, had required enormous effort before digital computers became available. Each comet in the dataset represented years of observation and calculation by multiple astronomers. Oort was looking at a specific property of each orbit. He was calculating what is called the original orbital energy, the energy the comet had before it entered the inner solar system, before the gravitational influence of Jupiter and Saturn could deflect it onto a slightly different path. The original energy tells you where the comet came from, how loosely or tightly it was bound to the Sun before its current passage began. What he found was a distribution that was not smooth. There was a concentration of comets with original orbital energies very close to zero, slightly negative. Slightly negative orbital energy means barely gravitationally bound to the Sun, coming from very large distances, tens of thousands of AU or more. There were far more comets with this characteristic than the expected distribution would suggest. It was not the distribution of comets scattered throughout the inner solar system or cycling from the Kuiper Belt. It was the distribution of objects falling inward for the first time, from a common reservoir at enormous distance. Oort recognised immediately that this required a source, not a disk source like the Kuiper Belt, because such a source would produce comets arriving mostly from the ecliptic plane. The comets in his dataset arrived from all directions. A spherical source was required. A source at great distance was required. A source from which comets could be perturbed inward by passing stars was required. The Oort cloud was born in that analysis, in that 1950 paper, from a dataset of a few dozen comets and a mind trained to recognise when a distribution is telling you something. 75 years later, the Oort cloud remains confirmed by precisely the same method, now applied to thousands of measured comet orbits rather than dozens, and supported by sophisticated computer models of solar system dynamics that Oort himself could not have run. The conclusion is the same. The numbers point to the same spherical source at the same great distance. The cloud is there. A comet's transit from the Oort cloud to the inner solar system is one of the slowest and most relentless processes in the solar system. Consider an object sitting in the outer Oort cloud at roughly 80,000 AU from the Sun. It is an icy body, perhaps a few kilometres across, perhaps 10. It formed in the inner solar system billions of years ago, was scattered outward by a gravitational encounter with Jupiter or Saturn in the chaotic early period, and has been orbiting at this distance ever since. Its orbit is nearly circular, carrying it slowly around the Sun on a path that takes approximately 1 million years to complete. For billions of years, nothing of consequence happens to it. The Sun is a point of light. Warmth is absent. Chemistry is frozen. It drifts. Then, over a period of perhaps 10 million years, passing stars begin to alter its orbit. Not dramatically. Not suddenly. A star passes at a distance of 2 light years. The gravitational perturbation at that distance is extraordinarily small, a tiny change in velocity, perhaps a few centimetres per second. The object's orbit shifts by an amount that would be undetectable to any instrument we have ever built. But the perturbations accumulate. Another star passes. The galactic tide exerts its slow, continuous pressure. The orbit becomes slightly more elliptical over millions of years. The closest approach to the Sun, the perihelion, begins to shrink, slowly, from a distance of 80,000 AU to 60,000 AU to 30,000 AU, dropping incrementally over many millions of years. At some point, the perihelion drops below roughly 15,000 AU, into a region where the galactic tide and stellar perturbations begin to interact with the Sun's gravity more strongly. The process can accelerate. Models show that under the right conditions, an outer Oort cloud object can go from a nearly circular orbit at 80,000 AU to a highly elliptical orbit with a perihelion in the inner solar system in a geologically modest amount of time, a few 100 million years. The object is now on a trajectory that will take it, over the course of its new orbit, from 80,000 AU at its far point to perhaps 2 or 3 AU at its close point, inside or near the asteroid belt. The fall from the far point to the close point alone takes perhaps 1 million years. The comet that arrives in our sky, visible and bright, has been travelling inward for longer than the genus Homo has existed. As it approaches the inner solar system, the Sun's gravity accelerates it. By the time it reaches the inner solar system, it is moving at tens of kilometres per second, heating rapidly for the first time in its existence. Its surface, which has never experienced significant warmth in 4.5 billion years, begins to change. Volatiles sublimate. The coma forms. The tail develops, pointing away from the sun as the solar wind pushes the escaping material outward. For a few weeks or months, the comet is visible. Astronomers observe it, amateur stargazers photograph it. Perhaps someone steps outside on a clear night and watches it cross the sky. Then it passes the sun, continues outward, and begins its return path. It may come back. It may be gravitationally deflected by Jupiter onto a shorter period orbit, trapping it in the inner solar system. It may be ejected entirely on a hyperbolic trajectory, sent out of the solar system forever. Or it may return to the Oort cloud, slowing over millions of years, and settle back into a long orbit, depleted by one passage but still largely intact. The one that was visible. The one someone photographed. The one that was an omen or a wonder or a point of light in a long exposure image. It spent 4.6 billion years in the dark and a few weeks in the light. The ratio is almost impossible to hold. The closing thought of this passage is not about distance, it is about belonging. The Oort cloud is cold, dark, sparse, and unreachable by any mission we can currently envision. By every human measure of relevance, it is the least accessible part of the solar system, the part most thoroughly removed from daily life, the part that most completely exceeds our ability to visit or directly observe, and yet it is part of the same system that includes this planet. Every frozen object in the Oort cloud orbits the same sun that rises each morning. Every one of them formed from the same original cloud of gas and dust that became the Earth, the Moon, Mars, Jupiter, and everything else in this system. Some of them carry molecules that were assembled in interstellar space before the Sun existed. Molecules older than any rock on Earth, preserved at nearly absolute zero in the outermost regions of a system we call home. When a comet crosses Earth's sky, it is a piece of that ancient outer structure visiting the inner one, a fragment of the solar system's primordial past, preserved intact for billions of years and then delivered briefly to the inner light. We have always watched comets. We have always felt, without always being able to say why, that they meant something, that they came from somewhere significant, that they were worth noting. That instinct was not wrong. They come from the edge of the solar system. They come from a place that is ours by gravity, ours by origin, ours by the simple fact that the sun we orbit holds all of it together in a gravitational embrace that extends nearly 2 light years in every direction. The solar system is not a small neighbourhood of 8 planets. It is a vast spherical gravitational domain, populated with trillions of objects most of us have never considered, extending nearly to the nearest stars, containing the oldest unaltered material in the system, sending messengers inward on million-year transits, sitting in quiet exchange with the galaxy that surrounds it. Everything in that domain orbits the same star you orbit. Everything in that domain is part of the same system you call home. The edge of that system is out there, in the dark, at a distance that light takes a year to cross. Cold, quiet, ancient, populated, and somewhere in that darkness, right now, another frozen object is beginning its long fall inward, disturbed by a passing star or the slow tide of the galaxy, beginning a fall toward the light that will take 1,000,000 years to complete. By the time it arrives, much will have changed here. But the solar system will still be here, the same vast gravitational structure it has always been, reaching outward in all directions to its quiet frozen edge. Good night.